welcome again. In this lecture, I will solve partial differential equations with the help of the Fourier transformation. And now you will see that this is your application of the Fourier transformation. Application of Fourier transform, infinite Fourier transform. Here I am only discussing infinite Fourier transform. So application of infinite Fourier transform. Let us find out the Fourier Sine transformation of del t upon del x2. Now the Fourier transformation of del t upon del x2 will be integral 0 to infinity. Then we will have del t upon del t upon del x2, and then as we are finding the Fourier Sine transformation, so we will have sine sx and then the integration with respect to x. Now let us solve this integral using the by-part integration. Now the integration of this one will be your del upon del x. Then we will have sine sx and the limits from 0 to infinity. Then we will have minus sine and the integral 0 to infinity. Now the again integration of this one will be your del upon del x, and the differentiation of sine sx with respect to x will be your s, and then cos sx dx. Now let us assume that del upon del x tends to 0 as your x tends to plus infinity or minus infinity. So, and you will see that in the most cases during my problems, for most of the physical problems, our del upon del x tends to 0 for your x tends to plus minus infinity. So if this condition holds, then you can say that your upper limit will be 0, and again for sine sx your lower limit will be 0. The first term is 0, and here we will get s integral 0 to infinity del upon del x cos sx dx. So again let us integrate del upon del x. So the integration of del upon del x will be u and cos sx, then the integral from 0 to infinity, then we will have minus sign, and again the integration of this one will be your u, and the differentiation of cos sx will be your minus plus. This will be your sin sx, and then we will have dx. Now again taking this condition that let u comma del upon del x tends to 0 as x tends to plus minus infinity, your upper limit will become 0 and the lower limit will be your cos 0, and cos 0 is 1. So here we will get the upper limit is 0, and for the lower limit our x is 0. So if you now here your u will depend on either x and t. So now your x is 0, so the lower limit will be, for the upper limit it is 0, and for the lower limit this will be your x is 0 and the cos 0 is 1. So cos sx. So the lower limit cos 0 is 1, and we will get u at 0. So u at x equal to 0 means minus u 0t. And this is this term u sin sx. This is the definition of Fourier Sine transform. So here you will get Fourier transformation of us. This is the definition of the Fourier transformation of u. That means Fourier Sine transformation of u. Thus, we have the result. The Fourier transformation of del t upon del x2 is equal to, so this is your minus plus, so this will be your s u 0t minus s square u s, and this will be a function of s and t. So this is the Fourier Sine transformation of del t upon del x2, and we will need this result in our problems. So this is our Fourier Sine transformation. Now let us find out the Fourier cosine transformation. Please note this formula. If we have fc, if suppose that we have to find out the cosine transformation, then we will get cos sx. Now integration, this will be your cos sx, and here the differentiation of cos will be minus, so this is your plus, again we will get sine sx. So again assume that let Suppose that u and del u upon del x tends to 0 as x tends to plus minus infinity. So you will see that for the upper limit will be 0 because del u upon del x tends to 0, and for the lower limit this will be your minus sign, and the value of del u upon del x at x equal to 0. So that means this now del u upon del x can be written as ux, and this value at x equal to 0, that means 0 comma t. Then we have this plus sign. Now again integrate this term using the by part integration. So this will be your u sine sx, and then the integration from 0 to infinity. Then we will have minus sine, and the differentiation of sine sx will be s times, and the integration of del u upon del x will be u, and the integration of the differentiation of sine sx is your s into cos sx, and then integration with respect to x. So here you can see that this is your ux 0t. Now again using this fact that u tends to 0 as x tends to plus infinity, the upper limit will be 0, and for the lower limit we have x equal to 0. So again upper and lower limit are 0. Now this s into s will be your minus s square, and then this is your Fourier cosine transformation of u. So this is your uc, and this will be your in terms of s, so we will write it s comma t. So we have another formula. Fourier cosine transformation of del t upon del x2 is equal to minus ux 0t minus s square uc st. So this is your formula for Fourier sine transformation, and it is for the Fourier cosine transformation. Now during the solution of the problem, please remember that we will use this formula when the value at u0 comma t is given, and we will use this Fourier cosine formula when the value of del u upon del x is given. If the value of del u upon del x is given at x equal to 0, then use this formula, and for the remaining case use this Fourier sine transformation. Also, the Fourier sine transformation of del u upon del t will be, now use the definition, integral 0 to infinity del u upon del t, and as we are finding the Fourier sine transformation, so we will get sine sx, and then integration with respect to x. Now as we are integrating with respect to x, so that means this t is constant, so we can take this t outside using the Leibniz rule of integration under differentiation, using the Leibniz rule of differentiation under integration sign. Now this left hand side is, now this bracket is your Fourier sine transformation, so we can write it as Fourier sine transformation of u. So that means Fourier sine transformation of del u upon del t is same as dus upon dt, where us means the sine transformation of u, and similarly the Fourier cosine transformation of del u upon del t is equal to du d, then the cosine transformation of u with respect to dt. So again we have these two formulae. So the Fourier sine transformation of del u upon del t means the derivative of the sine transformation of u with respect to t, and the Fourier cosine transformation of del u upon del t will be the derivative of uc with respect to t. Let us solve questions. So question number 1, solve the partial differential equation where now the conditions are, here my x is greater than equal to x is greater than 0, t is greater than 0, subjected to the condition u0t equal to 0, ux0 is equal to either 1 for 0 to 1, and this is 0 for x greater than 0. Now let us solve this question using the Fourier transformation. Please note that here as we have given the value of u x comma t at x equal to 0, so we will use the Fourier Sine transformation. So now we will use directly formula. We will not prove the formula using the applying the Fourier Sine transform. We get, now the left hand side will be fs del upon del t and the right hand side is fs del t upon del x2. Now please use the formula. So this was your del d us upon dt, where us means the Fourier Sine transformation of u, and this was your s u0t minus s square us at s comma t. This was the Fourier Sine transformation of del t upon del x2. Now u0t is 0, so this term is 0, so we will get du upon dt is equal to minus s square us at s comma t. So this is equal to dus upon us is equal to minus s square dt. This us is a function of st, so there is no need to write this one. So on integration, this will be your log us is equal to, now this will be your minus s square t plus some constant of integration, say log c. So log us upon c is equal to minus s square t. So you can see that your us will be c times e to the power minus s square t. So this is the Fourier Sine transformation of this function u. Now we have to find out the function u. So for that we will need this c. Say this is equation number 1. Also u0t, again from this equation you can see that this is your this term. Now if your s equal to 0, then you can see that this is your e to power 0 and e to power 0 is 1, so this is your c. Now because we have this condition, as now we have given this condition ux 0 is equal to 1 when your x is between 0 to 1, and this is your 0 when your x is greater than 0. Let us find out its Fourier Sine transformation. As ux 0 equal to this one, so its Fourier Sine transformation will be us 0. Now use the definition of the Fourier Sine transformation, and which is equal to 0 to infinity, then your function, and then function, and now t is 0, so this will be your 0, and then as we are taking the Fourier Sine transformation, so we will get sine sx and then dx. Now here you can see that the value of x, when the value of x is between 0 to 1, then your ux0 is 1. So that means this is your 1 when your x lies between 0 to 1, and for the remaining cases it is 0. So we can write it as integral 0 to 1. Now the value of ux0 is 1, so this is your 1, and sine sx dx. Now integration of sine sx will be minus cos sx divided by s, and the limits from 0 to 1. So this is equal to 1 upon s. So for the lower limit we will have 1, and the upper limit will be your cos s. So this is the value of us s0. Now us, this is your, this is your when t equal to 0. Now if t equal to 0, then this will be your c. Now thus you can see that here your us0 is c, and here your us0 is this one. Therefore our us0 is equal to c, and this c is equal to this term, which is your 1 upon s into 1 minus cos s. Therefore, our us is equal to 1 upon s, 1 minus cos s, and then e to the power minus s square t. Thus, we have evaluated the Fourier sine transformation of u. Now, if this is the Fourier sine transformation, then apply the inverse Fourier sine transformation. Therefore, your u x t will be 2 upon pi integral 0 to infinity us st. Then, as we are applying the inverse Fourier sine transformation, so we will get sine s x and then integration with respect to s. So this is equal to 2 upon pi 0 to infinity 1 minus cos s upon s. Then here we will get e to the power minus s square t sine sx dx. So this is your answer. So this is the Fourier sine. This is the solution of the partial differential equation. Now let us solve one more question. Please check calculation mistake. If there is any calculation mistake, then you can correct it. So this is your answer. And here this will be your, here you can see that the integration of sine is minus cos, and for the upper limit this will be minus cos, and for the lower limit this will be 1. So I think this is okay. And here your uxt will be 2 upon pi 0 to infinity us st, and so this is your answer. So let us solve one more question. So solve del upon solve this partial differential equation del upon del t equal to k times del t upon del x2, where your x is between 0 to infinity and subjected to the first condition is u equal to 0 at t equal to 0, and for positive x, and second case is your del u upon del t equal to minus k, or you can say minus mu, for x equal to 0 and t greater than 0. So this is your question. Here you can see that we have given the value of del u upon del t. So as the value of del u upon del t is given, so we will use the binomial. So we will use the Fourier cosine transformation. This will be your del u upon del x, not del u upon del t. So let us solve this question using the Fourier cosine transformation. We will apply Fourier cosine transformation because of this condition. So let us apply the Fourier cosine transformation on both sides. Then use our formula. So this will be your d uc upon dt, and now here the Fourier cosine transformation was, please remember your formula, and this was your minus del upon del x. This was your minus del upon del x at x equal to, or you can write it as minus ux. This was your at x equal to 0, and then plus, then we have minus sign minus s square uc at s comma t. This was the Fourier sine transformation, Fourier cosine transformation of a function. So now here the value of this minus ux, the value of this ux is equal to minus u. So this will be your minus minus plus mu. The value of ux is minus mu, so this will be your plus mu. And here we will get minus s square, and this is your cosine transformation of function u. So let us take this term on the left hand side, and this is equal to k mu. Now you can see that This is your linear differential equation of first order. dy by dx plus some function of s then into y equal to some constant. Now the solution of this differential equation will be, therefore integrating factor will be your integral e to the power k s square and then integration with respect to t. So this will be your e to the power k s square t, and solution is uc into integrating factor into uc is equal to k mu into integrating factor. This was your integrating factor e to the power k s square t, and then integration with respect to t plus some constant of integration, say c. So this is equal to, now if we integrate this term with respect to t, then this will be k mu, integration of e to the power x is e to the power x, and then integration with respect to t will be your k s square plus some constant of integration. And here in the left hand side we will have e to the power k s square t into uc. So your uc will be, now here you consider your k and k is cancelled, so this will be mu upon s square plus your c times e to the power minus k s square t. So this is your Fourier cosine transformation of the function u. Now let us find out this c, as the value of the function u is 0 at x equal to 0, as this was your 0. So that means on applying your Fourier cosine transformation, this will be your, I think this was your, the value of u is 0 when your t is 0. This was your 0. The value of u is given 0 when your t is 0, so this will be your u as 0 equal to 0 on applying the Fourier cosine transformation. Say, let us, this equation is equation number 1 and this is your 2. Now, this is your uc and this will be a function of s and t. Now, if you put t equal to 0 in equation number 1, if t equal to 0 in 1, then you can see that now the value of this term will be your 0 according to 2. So in the left hand side we will have 0. Now as our t equal to 0, so we will get c, and then as t is 0, e to the power 0 is 1, so we will get 1. So you can see that our c is equal to minus mu upon s square. So if this is your c, then our u c will be mu upon s square minus mu upon s square e to the power minus k s square t, or thus your cosine transformation of the function is equal to mu upon s square 1 minus e to the power minus k s square t. So this is the Fourier cosine transformation of the function u. Therefore, the solution, that means the inverse Fourier transformation, will be 2 upon pi integral 0 to infinity, then uc, and the integration with respect to cos sx, and then integration with respect to x, ds. So this is your answer. Just put the value of mu c. So if we put mu c, then we will get this mu outside, and in the bracket we will have 1 minus e to the power minus k s square t divided by s square cos sx ds. So this is the solution of the partial differential equation.